Welcome everyone. So today our speaker is Professor Daniel Cabra. Daniel is a professor at the University of La Plata in Argentina. Before that, he spent several years in Strasbourg in France, and he's currently visiting us for a few weeks. Daniel is an expert on condensed matter theory, many aspects, including strongly correlated systems, quantum magnetism, and low-dimensional systems. And today he's going to tell us about multiferroics.
Okay, thank you very much. Well, thank you for the invitation for these nice 3 weeks, and thanks also for the invitation to give this talk. So I will talk about a few papers we did on the one type of multiferroic systems. I think I can better move here. And so this is a collaboration I did with my main collaborator in La Plata, Gerardo Rossini. These guys in Rosario. They are also in La Plata, but they are half experimentalist, half theorist. And Armando Ligia from Bariloche joined the team recently. Okay, so what I'm going to talk about is contained in the title. So it's a model that connects the magnetic and the electric degrees of freedom via the lattice. Okay, and this is what I'm going to describe in detail. So, well, essentially, what are multiferroics? Well, I guess everybody knows. So there is coexistence of ferromagnetism and ferroelectricity, or any other of these 4 options. And the idea is that one should be able to switch, for example, electric polarization by a magnetic field, or a magnetization by an electric field, and this, well, has potential interest in the applications. And what I'm going to discuss is the magneto-electric coupling that appears when you have magnetic collinear structures. Okay, there are different types of multiferroic materials. Maybe I will describe some details later, but I will focus on these systems that have magnetic collinear structures. And I will, of course, play a little bit with the role of phonons. In fact, these are lattice deformations, to be more precise. And okay, so this is what we call the pantograph model, just to give it a cartoon picture, which I will describe. And what you can find in this very simple effective model is that you can switch P by H or M by E, and this goes through, at least in some one-dimensional systems, through fractional excitations. And at the end, I will say a few words about two-dimensional systems and higher spins. Okay. Okay. So we recently wrote a review article in this Journal of Applied Physics where we collected all these results. Okay. So what are multiferroics? Very briefly, just to summarize what I said before. So we have normally you have a polarization varying with electric field and magnetization with a magnetic field. Well, now you may have these crossed effects, and most of the systems that show this kind of intercorrelation between magnetism and electric polarization have these structures that you can see here. So there is these Jahn-Teller effects normally taking place, and most of them are these perovskite structures. And so, as I said before, I will focus in a particular subclass of which is still large, but it has some. Well, there are different classifications, but one is proper, improper, type 1, type 2. So I will focus on what I call improper type 2 multiferroics. And in this type of multiferroics, magnetization and polarization are intercorrelated. And the main common characteristics that caught my attention a long time ago, and that have to do with this classification and has to and will show up in the models we discussed, is that first of all there is a magnetic collinear ordering of the type up, up, down, down. in one direction if it is a one-dimensional model, or in 2 and 3. And this is really very common in all these systems here. And also there is a simultaneous jump of P polarization going down with the field, the magnetic field, at the same time as the magnetization jumps up, okay, in a kind of metamagnetic transition. So I first observed these effects in these systems. I mean, I found it in the literature. It's not that I have done any. I think it's first order. Yeah, in most of the cases. Yeah, it's a metamagnetic jump, and then at the same time polarization goes down. Yeah. And yeah. Yeah, I think so. Okay, so then I discovered that there were these manganite perovskites when there is this E-type antiferromagnetic order, which is just up, up, down, down in 2 directions. And okay, there are also 3-dimensional systems, the nickelates, that show similar magnetic structure, and also some transition that shows not all these facts have been observed, but in principle they should be there. And there are also these double perovskites materials, which are almost, in most of the cases, quasi one-dimensional, and they show large magneto-electric coupling. Okay, and this is, from our point of view, these are the most interesting because the models we are studying are closer to them. Okay, so let me show you some of the experimental results. So for example, this is one of these double perovskites, and you see this is P going down, this is H, magnetic field. So P goes down, just take a low temperature 2K, and at the same magnetic field, this M goes up. So this is the kind of observation that happens not only in this double perovskite, but in many of the other materials I have mentioned. And there is another interesting thing that we are studying now, that is, okay, you could think that this is magnetization plateau at low fields, and once you magnetize a system, you kill this polarization. So you have a big change in polarization when you go out of a plateau, a magnetization plateau. And the similar thing is observed in other systems that have a 1/3 plateau. Let me show you in the next slide. Maybe one next, yeah, this one. So here I recovered this figure that I have shown you before. So here is a variation of the polarization with the magnetic field. And you see here are the fields where you go in and out of this 1/3 plateau. Okay, so it seems that whenever you have some spin gap, let's say at some in some region, when you go out or in or out in any direction, then you have a big change in a large change in the polarization. This is another set of measurements. Again, delta M is large, goes up when P goes down. This is another of these double perovskites, which are quasi one-dimensional. Okay, so these are the observations, and the model we studied, I will tell you in a minute why this was the idea. So this is really a cartoon, okay? I'm not claiming that we are modeling perovskites, but the idea was that, so I was very familiar with the spin-Peierls transition. So whenever you have these magnetic units interacting, and there are some deformations that may enlarge or decrease the magnetic exchange here in this way. So this is first order expansion, and then you have this elastic energy. Well, it is well known that in one-dimensional systems, this has spin-Peierls instability. And I was very familiar with this, and with this system in a magnetic field, and I knew that something of what I have shown before, like for example, this magnetization increases when you go out of the well, in this case of spin gap region, so magnetization zero plateau. So then we proposed a model. Well, this was also a little bit, then we changed a little bit the original model, but the idea is always the same. So the idea is that you have some cartoon of the octahedra or some structure, 2D structure or 3D structure, that whenever deforms in one direction, it also deforms in the other direction with some connection, some phenomenological connection between the way these guys get closer and the guys get farther away. And if there are electronic clouds, for example, if you have different charges here and there, then the electric polarization will change. So this was inspired in some materials that I have already. Let me just spend a few seconds. I think it was inspired in some proposals to describe these delaphocytes. Of course, this in the end turned out to be 2D, but in the original pictures they were trying to describe this in a way that looks very close to what I have just drawn. So these atoms S2 were having different charges up and down, and this was generating these local electric dipoles. Okay. So I think we are few, and it would be better if you have questions, please interrupt me. So maybe more helpful for everyone. To have this guy here? So essentially, this is the usual model that you propose when you have things that can get wider, farther away or closer, just computing the overlap. I'm not sure you need. No, not for this. There are other types of multiferroics where you do need this spin orbit. But here I think it's simply you distort the lattice and then overlaps, wave function overlaps get farther or closer. And well, okay, so this was a standard spin-Peierls model. And what we added to this was this idea here, that is that you could have at the origin some antiferroelectric ordering. So the red arrows here are the electric dipoles, and the black are the magnetic ions. So the idea is that if you have, for example, just one case, you have some antiferroelectric antiferroelectric ordering at the beginning, which leads to no polarization, net polarization. With this deformation, then you will get some either up or down net polarization. And the way to model this Z component of the local dipoles is connected also to this way in which things distort. Okay, so this alpha and beta will be small parameters, and they will be connected in some phenomenological way. And this sigma tells you what was the original ordering of the dipoles. And then, of course, once you have these dipoles, then you have to include this dipole interaction. Of course, well, of course, I don't know, but at least in our cases, you don't need to keep many orders here. In the case, very fast to zero, so first and second coupling, neighbor couplings are enough to deal with the physics. Okay, so this is why we called it pantograph, no? Because pantograph, I don't know, this was a toy when I was a kid, but every time I give a talk, nobody knows about pantographs. Yeah, so maybe I'm older than everyone, or it was some toy that was more common in Argentina. I'm not sure. Anyway, so it's not really, what we have here is not really this kind of pantograph, because this distorts all together in the same way. But the idea that you squeeze one direction and then you get larger the other one is at the root of this. And then I'm just repeating everything before. So we have spin-Peierls Hamiltonian, dipole-dipole interaction, and the dipoles are coupled to the lattice in this way. So you see the coupling between the lattice and the spins is here, between the spins, between the electric dipoles and the lattice is here and also in there, and you have this elastic term. So it's an indirect coupling, okay? And essentially, okay, what happens if you have only the first term? So if you let us focus on this term. So this Hamiltonian here, the spin-Peierls Hamiltonian in a magnetic field, which is what we are interested in. And this was something we already studied a long time ago. And also other people, for example, already in '98, they have studied, okay, this is us, we have studied the spin system plus these deformations in a magnetic field. And you see that there is this, so some spin gap and then a jump in the magnetization. Okay, this is finite size system, results in the image. And when you go out of this m equals 0 state, when you start to polarize to create magnons, then you see that these magnons, for example, this is a situation when you create one magnon and you look at the equilibrium state for one magnon, then you see that this divides into two regions when you have two solitons. Essentially, each magnon decays into two spinons, as it is expected from other analysis. And this was already studied also. You see in copper germanite studies, this guy made some simulations, and here you have, I don't know how many, but many magnons, all of them decaying into two spinons. And so essentially the idea was to check what was going on once you add to this system the electric part. And so expanding the dipole-dipole interaction to first neighbors, we have checked that second and third neighbors introduces some interesting things, but do not change what I'm going to say now. And so we have this term, which is dipolar phonon-induced coupling. Of course, this term is can be forgotten in front of this one, but the fact that this so these are so you have magnetic units which are coupled in this part here, spin-Peierls, and then you may have originally some electric dipoles that we consider Ising variables. Okay, so this is what I'm telling now is for the case where you have some antiferroelectric background. Okay, so these sigmas at the end of the day will be plus minus 1. Okay, plus minus 1 in one way or the other, and then you have the deformation that makes the value of the dipole larger or smaller. Okay, this just provides the direction of the dipole, electric dipole. Okay. Well, it changes a little bit because, okay, first of all, this is an expansion of, so in principle, the whole expression is here. And here you have, you see, if you put PZ in this way, so in this expression, you have the same idea. So it goes linear if they get larger or shorter. So the modulus of P enlarges or gets smaller. But then you put it here, and then you have 1 over R cubed. And these R also have deltas. So you have to be consistent in the expansion. It's not a big deal, but it's not exactly the same way, okay, because it appears also here. And so, okay, so take the minimalistic expression, and okay, and then we know that let's say case 1 magneto-elastic coupling dominates because there are many variables. So we say, okay, let's study, let's put the Ising variables, the dipoles, electric dipoles as spectators, and study what happens with the magneto-elastic part. And the magneto-elastic part, we know that the system has a dimerization with a spin gap, and it can lead to this dimerization or one side shifted. Okay, so you have twofold degeneracy, and so we decided to write it this way because, well, for some technical reasons, later we will have other modulations, but in this case it's a bit too much to write it like this. It's -1 to the x or -1 to the x plus 1. Okay, but essentially this is a nice way to write it. The deformation is dimerization plus minus something, and you have two values of P because of this twofold degeneracy. And so when you create a magnon in the system, you will get a deformation that splits your original ground state into this. And what means this picture here is that here you have one of the ground states and here you have the other one. Okay, so the system splits into two halves. One, well, I think I managed to put it here. So this region has this deformation where these guys pointing up got larger. So you will have a net polarization pointing out. And in the other region, when you have the other ground state, so because these spinons are domain walls that separate the two ground states, here you get the other deformation, okay, shifted by one. Now the guys which were getting larger here are getting shorter, okay, so now we have a PZ pointing down. Okay, so this is a twofold degeneracy that you had at the beginning that now comes into the game in this excited or one magnon state. And this will happen with one magnon or any other of magnon, any number of magnons. And then what you can conclude is that if you compute P in this system, this area with this area will cancel out and P goes to 0. Okay, so this is the argument. Okay, why these two guys will be equidistant? Okay, this is energetic reasons. Okay, I will say more later, but this is also studied with DMRG, and this is clearly supported. So essentially what I'm saying is that if you can compute the total PZ in this state, you get 0, okay? So you get, for one ground state you get plus something, for the other ground state you get minus something, and when you get half and half, this gives 0. So essentially, the end of the story is that, so this is spin-Peierls. So you have spin gap, and magnetization goes up with the field. And what I'm telling you now is that here you start increasing magnetization by creating magnons that split into spinons, and then P goes down. As soon as you start creating one spinon or any number of spinons, any number of magnons that split into an even number of spinons, then P goes to 0. Okay, so there is this is one of the first things we wanted to describe, which is that you have a magnetic jump together with a drop-off of the polarization. And the mechanism here has to do with these guys. And okay, so this is DMRG, and DMRG, this is what happens with this is magnetic field. This is what happens with this magnetization. And as soon as this guy starts growing, P goes to 0. Okay, this is a kind of simplified model because this dielectric variables are Ising variables. Okay, so one has to be, one could try to do a better model for the electric part, but in this description, this clearly works. Okay, so first important result is that one can tune P to 0 by just going out of this plateau. Okay. So what happens in the other case if we say, okay, let's study the ferroelastic part of the Hamiltonian, so the dipoles with this coupling to the elastic deformations, and we put okay, so we study this in the presence of an electric field, and then you see, well, there is a whole phase diagram, so you can vary the coupling between the dipoles and the electric field, and you find that for lower, very low electric fields, you have this dimerized coupling, but if you go up with the field, then you get other arrangements of these electric dipoles. Okay, and if you compute the magnetic ground state here and there and up there, then you see that depending on the region, so for example here you see that you have a small 0 plateau or bigger depending on the values of the alphas, and almost nothing else. But if you go up here, where you get this quadrumerized arrangement of the electric dipoles, not any longer this dimerized, but quadrumerized, then you can have this 1/2 plateau, okay, and even wider if you increase the ferroelastic coupling, okay. So, okay, that's another effect, and the other way around. So now you shift, you move the electric field, so you go from this state to this state, and then you will go to some situation where there is no 1/2 plateau to a situation where there is one, okay. How I'm doing with time? Okay, I'm doing well, okay, yeah. Okay, so then that's, okay, that's maybe a bit not very clear in this picture. I had a better one, but if you go, so the idea here is to move magnetization with an electric field, essentially. Let's check here. So essentially, I want to go from this deformation pattern to another one, and in one case, I will have this magnetization states, and in this case, I will have these guys here. Okay, so I can play around with the electric field and move the magnetization from one value to the other. Okay. So this will be the other way around, but okay, here you need to go up in field to be in this plateau, and this is probably in any reasonable material will imply very large fields. So this is not so interesting from the experiments or the possible applications. So essentially, the most important part I want to emphasize here is that this reproduces what is observed in experiments. And this, okay, you can play around if you like, and claim that you can change the magnetization with the electric field too. Okay. Okay, so far we were able to reproduce. Sorry. We were able to reproduce this issue, but I also told you that in most of the materials there was an ordering that was observed, that it was up, up, down, down in the magnetic part, and in order to make contact with real systems, what we did was to make it better, or let's say more interesting, the spin part, adding second neighbors, and also adding an SZ anisotropy, so kind of easing like anisotropy in the magnetic part. So this is no longer SU2 invariant, but you have some gamma, or well, gamma or 1/delta, depends on how you want to call. But we're keeping these issues that we discussed before. So this gamma equal 1 is SU2, and gamma equals 0, because it's 1/delta, is easing. And we have found that in certain region where a large easing coupling, then you recover this up-up-down region. Okay, so there is a whole phase diagram, but the interesting thing is that, okay, what I discussed before was this this part here, and now if you look at easing like region around here, see, this is for gamma equal to 1/8, so delta equal 8, so pretty large easing anisotropy, and nearest neighbor in the magnetic part of point HI1, then you get this up, down, down ordering that is also observed. Okay, so this is for 1D. Okay, I will skip this. Yeah. Mm-hmm. No, so here I broke SU2 invariance in the magnetic, and it's even more close to experiments. So magnetic part, so the dielectric part is easing. Let's keep it easing. As for the magnetic part, I started doing SU2 because this is what I knew when I started. But then we say, okay, let's consider more easing like the magnetic part. And this is motivated from the experiments because they see a crystal field, important crystal fields. So it's probably better to. Yeah, exactly. So that's why it's, and indeed, taking into account this easy axis crystal field term, then you get this up, up, down, down magnetic ordering, okay? This is the MRG. There are many things. There are whenever you can do bosonization. There are combination of different things, but yeah. There are also results from previous studies. No? So this line has been thoroughly studied. Also this one, I mean, this aniphase is well known from Ising with next nearest neighbor. So there are, so the new things we studied is around here, just to, we were looking for this up, up, down, down ordering, which is what is called here aniphase. No? And yeah. J2, you mean? Yeah, okay. It's, you could also make it, but it doesn't change anything. This we knew from previous studies. So essentially, you see here you have the version of, this is a way to write J2 over J1. So you could say this deforms, but the zigzag don't change, or the other way around. One changes and the other not. But even if you take deltas here, it will be, the physics will be the same, okay? Okay, okay, this is 1/8, so delta equal 8, so Ising anisotropy, and you see the same story going on. M goes up, so this is the MRG, and P goes down. And okay, you can look at the structure, what you find in the different domains. And now if you look at the magnetic, of the magnetic units, you will be that you have up, up, down, down states here. No more singlets, as in the case of pure Heisenberg SU2 symmetric. And okay, so the idea, just to sell the product, is that you have some, imagine that you have a small polling field and you have one electric polarization in your system here. And then you create a strong magnetic field step to go here, and then you kill this polarization via this soliton lattice, and then with a tiny signal in the opposite direction, you get the opposite. Once you turn off, you go back to the polarized region with the other polarization. Okay, that's just to play around. Okay, so I will not say much about higher spins because we are still in the middle of these things, but just to say that there are interesting things. For example, this is a spin 3/2, and we have seen that there is some deformation region where you have this spin-Peierls mechanism, so there is no deformation for small coupling between the lattice and the spins. But if this becomes larger, then you have this ferromagnetic, antiferromagnetic coupling. And in this region, we expect to be able to have similar things like here, if we include also the electric part. But this has not been done. Okay, and also for spin 1, similar things observed. This is for spin 3/2, so if anyone is interested, I will be here still two more weeks. And so now trying to go to more larger dimensional systems, we looked at the case of nickelates. I got the inspiration from this review paper by Cheong and Mostovoy on these nickelates, that they were suggesting some deformation of this type. So we extended the model. So this is these are all the nickelates that have been studied with well, different tolerance factors, means that the different sizes of the atoms. And if you go down in temperature, first you go to from paramagnetic metal to an insulator, but then you go to an antiferromagnetic insulator, and BD is No, this I don't know. I don't know. You mean the one here? I'm not familiar with this one. I'm sorry. So because I was interested to come here to start from the deformed state and then see if similar things. So really low temperature. This is what we are doing. No? Really low temperature, and starting from this distorted situation and what happens if you put a magnetic field. And okay, so 2D is more complicated, so we simplified the model by now putting also the magnetic units as Ising. Okay, so this is an Ising magneto-elastic spin-Peierls and Ising dipoles, electric dipoles. Okay, so this was Monte Carlo simulations, and so there were some studies where you could see that well, we are doing something in 3D, but this is for the moment not finished. But you see that you have two possibilities. Either you create these blocks of 4 spins up and 4 spins down. If you look in the two directions, you see up, up, down, down in both. But there is another possibility, which we call the stripe. This is a checkerboard, and this is a stripe state. Here you also see up, up, down, down, horizontally or vertically, but they are shifted, okay, from one line to the other. And what we discovered, this is what happens if you just consider Ising magneto-elastic in 2D, that you have this double degeneracy, but once you put the electric dipoles in some way and the interaction within these electric dipoles, then this state here is selected, okay? And if you further put a magnetic field, well, this is without electric dipoles. If you put electric dipoles, you see you have a polarization for low fields that gets killed with a magnetic field at the same time as the magnetization. So this violet is polarization and orange is magnetization. And here you see that magnetization goes up and polarization goes down in a similar way as it was observed in the experiments, okay? Okay, so we haven't studied this transition, but it looks first order. And okay, well, this is what is observed. So you have this state, polarized state for low fields, magnetic fields, which gets depolarized and magnetized when you increase the magnetic field. And okay, you should observe these structures both in the spin channel, the up, up, down, down, and the formations in this particular way. And I think I don't know. We haven't studied. You mean? Yeah, yeah. This is a very interesting question. What happens here with this? How do you go here in this? So yeah, this is very interesting, but we haven't looked at that. Okay, so just to conclude, okay, so essentially I repeat what I said before. So this is a model that couples these two guys, magnetism and ferroelectricity, by the lattice in this simple cartoon way. And both 1D and 2D models, at least those we studied, reproduce some basic experimental facts. This dipolar moment switch off with a magnetic field and this magnetic stripe up, up, down, down ordering. And this is what you observed numerically. Okay, one could look also. Okay, this is something funny in Spanish, which I cannot explain. But, this is a magneto-electroelastic excitation, so it should call meons or muons or something like that. And if you look at the structure of what's going on, then you see that you have these, as before, you have these solitons. Now you have also, whenever you have a soliton, you have some electric also thing going on and some magnetic thing. So there is kind of three things that put together in this separate regions that separate one area from the other. So I talked already about that. So I think this is more or less, well, I have a couple of more things to say, but okay, so there are many open routes. Some of them we are looking at or we would like to look at. And one of the questions is what happens if you take seriously this lattice deformations delta and study what happens if there are quantum phonons in 1 and 2 diversions. This is something I don't know how to do, to study the effect of external strain. That is also studied experimentally, but would be very interesting. This is another idea, which is to see what happens now if you have, instead of Peierls model, Howard-Holstein. So to study what happens with these systems when you have, instead of spin system, charge systems. And it connects to this next line here, in which I want to interest people, which is a very strange thing. These are polar metals. I don't know if you have heard about them. There is an old paper by Anderson and Blount where they claim that this could be observed. And recently there are experiments in these materials and others where they say that they observe something that is conducting and has some electric polarization. So, and then whenever you say that, they say this cannot be, because conducting electrons will how do you say, screen the polarization. Well, okay, that's an open thing. I'm trying to look at the models, but there is this paper that claims that it should be possible. I don't know why. I don't understand why it should be possible. What I understand is that it's impossible, essentially. But these guys claim that they, in some situations, they get some reduced polarization, but still some polarization, and on top of it, conducting. So all of this is to be checked. But what I'm saying is that that's an interesting open issue. There are also superconducting polar situations, which, okay, if we don't understand these ones, we will not understand the superconducting case. And then we are working on this, yes, to make contact with the experiments in nickelates and also in field theory formulations. Do we still have a few minutes? Or yeah, okay, so let me say, so one sad story is that I was supposed to become director of this institute in Kigali, in Rwanda, in July this year. So I was selected by the committee, but somehow something went wrong in Africa, and it is on hold. So this was some advertisement I had at the end of my talk, but okay, now it's, you should cross it. But I wanted to come here. Okay, so just repeating what I was saying before. So this is a material where they have observed, apparently they claim that they have observed polar metal. And okay, so they propose some Hamiltonian, which we are studying. I'm trying to understand how this could lead to these two things they claim they get. Of course, the analysis here is very, very simplified, so this has to be done better, but this is just to motivate the issue. And okay, and no, this is okay, and this is the end, because I had another version that. So I think that's all. Thank you very much for your attention.
Okay, thanks, Daniel. Questions?
I just wanted to ask, if you are thinking in terms of field theory, do you have continuous model that represents similar properties, like?
So in the 1D case,
yeah,
this is how I started, because I was familiar with this spin-Peierls. I'm afraid I have nothing here, but I can, let me. So in the case of spin 1/2,
do you have something like long lengths?
Yeah, in the case of spin 1/2, so the spin-Peierls system is Sine-Gordon, okay? Sine-Gordon theory. This is why you have these solitons there appearing in pairs. This is a sine.
But this is without that. So
Without dipoles are spectators. So I'm saying let's consider that magneto-elastic coupling dominates. Okay. So I take the continuum limit of this theory, and then I add on top of this the Ising variables. Okay.
No, but how it looks in one wavelength mean?
If you put everything,
Yeah.
no, I don't know, because here this, you know, we are not taking seriously the Ising variables, the dielectric dipoles, the dipoles. So to answer your question, one should work out a continuum limit of both sectors. This we haven't done.
I wanted to ask about this example where you had these different domains with different polarization. They all had the same size. Is that because it's a finite size system?
Well,
because
we can work out only finite size systems with periodic boundary conditions. Yeah, but in principle, these guys should be equidistant by energetic reasons. So if you look at the continuum theory, the Sine-Gordon theory, so these the spinons repel each other, and then that's why you have two regions with the same size. Mm-hmm. At least theoretically, if you use periodic boundary conditions, but I guess that this will happen. That's a good question. I don't know.
That's true even in the model with just short range interactions when you
yes. Yeah.
Any further questions?
Okay.
If not, let's thank Daniel again.
Thank you.